Jetpack Compose makes it easy to implement designs with just a couple of layout concepts. But what if your requirements are more complicated? In this episode, we'll take a look at more advanced layout concepts and how they can help you take your design implementations to the next level. In the previous episode of our Math Skills series on composed layouts and modifiers, Yolanda talked about the layout phase of Compose to explain how modifier chaining order and incoming parent constraints impact the composable they're passed to. Today's episode, we zoom in even more on the layout phase and constraints, cover them from another perspective, how to harness their power to build custom layouts in Compose. To build custom layouts, we'll go over what the layout phase is capable of, how to enter it, and how to use its subphases, measurement and placement, to your advantage for building flexible custom layouts. After that, we'll cover two important rule-defining Compose APIs, Subcompose layout and Intrinsic measurements, as the last two missing pieces of the layouts puzzle. These concepts will provide you with additional knowledge to build intricate designs with very specific requirements in Compose. In the previous episodes, we talked about how Compose transforms data into UI via its three phases: composition, layout, and draw, or what to show, where to place it, and how to render it. But as the name of our series suggests, we're mostly interested in the layout phase. However, the term layout in Compose is used well for a lot of different things, and might seem confusing because of its many meanings. So far in the series, we've learned the following usages. Layout phase, one of three phases of Compose where element sizing and positioning is defined. A layout, an abstract term used to quickly define any UI element in Compose. A layout node, a visual representation of one element in the UI tree, created as a result of the composition phase. In this episode, we'll also get to learn a few additional meanings to complete the whole layout circle. Let's quickly break them down first. A more in-depth explanation of these terms awaits later in the episode. Layout composable, the core component of the Compose UI, which creates and adds a layout node in the Compose UI tree. Layout function, the starting point of placement, which is the second substep of the layout phase that places children in the parent layout. Layout modifier, a modifier that wraps one single layout node and allows sizing and placing it individually. Now we've seen the different definitions, let's go over them one by one, starting with the layout phase, and zoom in on it. As mentioned, during the layout phase, each element in the UI tree measures its children, if any, which also enables the parent to decide on its own size. And finally, it places the children in the available 2D space. Every out-of-the-box layout in Compose, such as row and column and many more, handle all of this for you automatically. But what if your designs require non-standard layout, for which you need to go custom and build your own layout, like this complex-looking time graph from our jet lag sample? That's precisely when you need to know more about the layout phase, how to enter it, and how to use its subphases of child measurement and placement to your advantage. So let's take a look at how we can build a custom layout in Compose from a given design. Let's go over and explain the most important basic steps for building a custom layout. However, if you wish to follow a detailed step-by-step video guide on how and when to create a custom layout from a complex design, please take a look at the Custom Layouts and Graphics in Compose video, or directly explore the custom layout from our jet lag sample. You can also find the links in the description. Calling the layout composable is the starting point of both the layout phase and building a custom layout. It accepts a composable content as its children and a measure policy for measuring and positioning its elements. All higher-level layouts, like column and row, use this composable under the hood. Layout composable has currently three overloads. Layout for measuring and placing 0 or more children, which accepts one composable as content. Layout for leaf nodes of the UI tree with precisely 0 children, so it doesn't have a content parameter. And layout that accepts contents list for passing multiple different composables. Once we enter the layout phase, we see that it consists of two steps: measurement and placement in that specific order. Sizes of the child elements are calculated during the measure pass, and their positions during the placement pass. The order of these steps is enforced with Kotlin DSL scopes. During measurement, the content of the layout can be accessed as measurables, components that are now ready to be measured. Inside layout, measurables come as list by default. Depending on the requirements of your layout, you could either take this list and measure every item with the same incoming constraints to keep its original predefined size.
or tweak its measurements as needed by copying over constraints you wish to keep and overriding the ones you wish to change. A very important feature of the layout phase is single pass measurement. This means that a layout element may not measure at any of its children more than once. Single pass measurement is good for performance, allowing Compose to efficiently handle deep UI trees. Measuring a list of measurables would in return give a list of placeables, or a component that is now ready to be placed. The placement step starts by calling the layout function and entering the placement scope. At this point, the parent layout will be able to decide on its own size, for example, by summing up the widths and the heights of all its child placeables. Placement scope now allows us to use all placeables that came as a result of measurement. To start placing children, we need their starting x and y coordinates. Once we define where we want the children to be positioned, we call place to conclude with the placement pass. And with that, we end the placement step, as well as the layout phase. Your custom layout is now ready to be used and reused. Using the layout composable to create a custom layout enables you to manipulate all children elements and manually control their sizing and positioning. However, there are cases when creating a custom layout just from controlling one specific element is an overkill and not necessary. In these cases, rather than using custom layouts, Compose offers a better and simpler solution, the layout modifier, which allows you to measure and lay out just one single wrapped element. Let's look at an example where a UI element is being squashed by its parent in a way that we don't really like. We want just one element in this simple column to have more width than the parent is enforcing by removing the surrounding padding, for example, to achieve edge-to-edge appearance. To make the third element control itself and remove the enforced padding, we set a layout modifier on it. The way it works is very similar to the layout composable. It accepts a lambda that grants you access to the element you're measuring, passed as a single measurable, and the composable's incoming constraints from the parent. You then use it to modify how a single wrapped element is measured and laid out. We then change this element's maximum width in the measurement step to add some extra DPs.
And then we place it as we originally intended.
As we said previously, one of the strengths of the Compose is that you can choose your own path when problem solving, as there are usually multiple ways to achieve the same thing. If you knew the exact static size you want for this element, another approach would be to set require width modifier on it, so that the incoming constraints in the parent layout don't override its set width and instead respect it. In contrast, use of regular width modifier would have the set width overridden by the parent layout and incoming constraints in the measurement phase.
Now that we've covered how you can use the layout phase and the composable for writing your own custom layouts, let's take a step back to Compose phases. In earlier episodes, we talked about the phases of Compose and the rule of their precise ordering: composition, layout, and drawing. The layout phase then breaks down to measurement and placement subphases. While this applies to the vast majority of layout composables, there is one rule-breaking layout that doesn't follow this schema, but with a good reason: Subcompose layout. Think about the following use case. You're building a list of 1,000 items that simply cannot fit on the screen at the same time. In that case, composing all these child items would be unnecessary waste of resources. Why compose so many items up front if the majority of them cannot even be seen? Instead, a better approach would be to measure all list items to obtain their sizes, then based on that, calculate how many items can fit the available viewport, and finally, compose only items that would be visible. This is one of the main ideas behind Subcompose layout. It needs to do the measurement pass first for some child composables, and then secondly, to use that size information to determine whether to compose other children. Meaning the measurement step in the layout phase needs to happen before the composition phase of some children. This deferred composition is called subcomposition, and it is precisely why lazy components are built on top of Subcompose layout, which enables them to add content on demand while scrolling. Box with Constraints also uses Subcompose layout under the hood, but this use case is slightly different. It grants you access to incoming constraints like max height from the parent, which are not available in regular layouts. This is because the measurement step of some children is done before the composition of others. You can then use obtained constraints to decide whether to compose a child or not. As Subcompose layout changes the usual flow of Compose phases, there are certain costs and limitations when it comes to performance. Therefore, it's very important to understand when Subcompose layout should be used and when it's not needed. A good quick way of knowing when you might need Subcompose layout is when at least one child's composable's composition phase depends on the result of another child's composable measurement. We've seen valid use cases for this in lazy components and box with constraints. If, however, you just need one child's measurement to measure other children, you can do so with a regular layout composable. The second rule of Compose we previously mentioned is the single pass measurement in the layout phase, which helps greatly with overall performance of the step and the layout system in general. Think about the amount of recompositions that can happen in a short time and how limiting the measurement of the entire UI tree can improve the overall speed. Therefore, you should only attempt to measure your children once when writing custom layouts. In fact, manually trying to measure children twice throws a runtime exception. However, there are use cases when the parent layout needs to know some information about its children before measuring them, so that it could use this information for defining and passing down constraints. And this is precisely what intrinsic measurements do. They let you query children before they're measured.
Let's look at a following example. We want this column items to have the same width, or to be more precise, have each item's width as that of the widest child. In our case, the and modifiers item. But we also want that child to take as much width as it needs. So our first step doesn't really work. Each item takes only the space it requires. We can try out the following. However, this expands every item and the parent column to the max width available on the screen. Remember, we want the width of the widest item for all items. So as you can tell, we're aiming to use intrinsics here. By using intrinsic size max on the parent column, we're querying its children and asking, what is the maximum width you need to display all of your content properly? Since we're displaying text and the phrase and modifier is the longest, it will define the column's width. Conversely, if you need to use intrinsic size min, the question will be, what is the minimum width you need to display all of your content properly? In the case of text, the minimum intrinsic width is the one that has one word on each line. So you can use a combination of both min and max on width and height to get your desired behavior. However, intrinsic measurements don't really measure children twice. Instead, they do a different kind of a calculation. You can think of this as a pre-measure step that is cheaper and easier. So while this doesn't exactly break the single measurement rule, it does bend it a little bit. When creating a custom layout, intrinsics provide a default implementation based on approximations. However, sometimes this might not work for you. To specify the intrinsics of your custom layout, you can override all of the values inside the measure policy.
We've covered a lot today. All the various meanings of the term layout and how they relate to one another, how to enter and control the layout phase to your advantage when building custom layouts, and then we concluded with Subcompose layout and intrinsic measurements as the additional APIs for achieving very specific layout behaviors. And with this, we conclude our Math Skills series on Compose layouts and modifiers. We hope you've learned new things about Composed, renewed old knowledge, and most importantly, that you feel much more prepared and confident to migrate everything to Compose. And of course, don't forget to subscribe to our channel for more updates.